Hello everyone, my name is Tito Spadini and I will present to you the work entitled On the Application of SEGAN for the Attenuation of Eagle Noise in the Speech Sound Source Localization Problem. Before starting the presentation, let me point out the order of topics that will be discussed throughout the presentation. I will start by defining the contribution of this work, and then the motivation for this work will be exposed. Then, the sound source localization and denoising problems will be explained, as well as how denoising can help the sound source localization. To better understand the operation of the SEGAN technique for denoising task, GAN will first be explained, and then SEGAN will be explained. So we will move to the project pipeline to understand the steps taken, and finally I will bring some results which will be discussed and show the conclusions. The contribution of this work, which will be exposed throughout this presentation, is the accomplishment of the task of denoising through the combination of cascade techniques formed by SEGAN and log-MMSE, which, except perhaps for the training stage, is not computationally costly during the denoising process itself. And yet the results were promising and were enough to give a noticeable improvement to the sound source localization problem. We used the last signal processing cup as motivation. Its theme were search and rescue with drone-embedded sound source localization. A solution like this could increase the chances of successful rescues after events like natural disasters. For the sound source localization problem, we consider a plane wavefront, and the sound is detected by each microphone with a delay. As shown in the figure, for 2D scenarios, the source detection relative to a given reference point, such as a microphone 1, is parameterized by theta. For 3D scenarios, by theta and phi, representing the azimuth and the elevation angles respectively. After making delay corrections for all microphones, the semblance is calculated by the cross-correlation equation displayed. From the calculated values, the semblance panel is generated, displaying a level of similarity for each region indicated by the azimuth and elevation pair. Higher values are indicated by yellow tones, while the dark blue tones indicate lower values. The small black X indicates the correct location, and the red circle is the prediction. Because the signals are highly noisy, the prediction was made in error. As we can see, apart from the prediction being far from the actual location, there is not even any region of high similarity around the vicinity of the correct location, which can be observed by the almost absence of yellowish region around the black X. The problem to be solved by this work is to obtain the concentration of the greater similarity to the region around the correct location on the semblance panel. To achieve this, denoising methods will be explored. The two denoising methods used in this paper are the Speech Enhancement Generative Adversarial Network, called SEGAN, and log-MMSE, which is a classic technique based on mean square error. The different scenarios were built based on 3 different speech audios in 8 channels, 44.1 kHz and 16 bits wave files. The noise involved come from the 4 drone engines and also the wind. and the SNR values used are between -21 dB and 24 dB. Scenarios with different noise levels were created artificially. Each speech audio was mixed with noisy audio made up of drone motors and wind, and a different audio file was produced for each scenario of different noise intensity. Before we talk about SEGAN, it is important to understand its basis, the gun. It is a competitive game between two players, Generator G and Discriminator D. Each player is a neural network, but their goals are opposite. The gun framework is based on supervised learning and therefore relies on a dataset-based training step, while G tries to generate counterfeit samples that are good enough to fool D. And D tries to become the best fraud identifier. During the iterations, samples of G get closer and closer to different samples from the real dataset, and D increasingly identifies the classification of samples more and more correctly. It is noteworthy that it's a very computationally expensive approach that uses deep learning methods, and preferably it may be convenient to use at least one powerful GPU to perform the training. SEGAN uses autoencoders to perform the denoising process, specifically for voice. In order to preserve higher audio quality during the denoising process, which can damage relevant parts of the speech signal if the process is not carefully applied, there are connections between coding layers and respective decoding layers in the autoencoder. Based on a dataset consisting of samples of clean audio and its corresponding noisy versions, the network learns what characterizes the part of interest of the signal, which in this case is a speech, and removes the rest, which is interpreted as noise. With the trained model, the network input is simply the audio to be denoised, and the output will be the clean audio version. The pipeline of this work begins with the preparation of audios, which come from the Dragon dataset, used in the latest edition of IEEE Signal Processing Cup. This step consists of downsampling to 16 kHz, normalizing all channels based on the highest peak of full audio, considering all channels, and decomposing audio by channel to obtain 80 wave files of one channel each. Then, denoising is performed, which was done using three different approaches, one with SEGAN, one with log-MMSE, and one with the combination of both methods. After denoising, clean signals are used to generate the semblance panels, and then the Great Circle Distance, GCD, is calculated, which is the measure used to assess if the prediction is correct. Here we can see the semblance panels for the noisiest cases, before and after each method. It is more convenient to have a smaller yellowish region, and more importantly, such a region should be only around the black dot, which indicates the correct direction. This helps the estimation, indicated by the red circle, to be closer to the correct location. The panels in the first left column are noticeably damaged by noise. After applying SEGAN, you may notice the appearance of a region of high similarity around the correct location point. However, It should be noted that while the minus 19 dB case indicates a very convenient result, the minus 21 dB case results in an even worse prediction than the one without the denoising process, even with the region of similarity nearest to the correct location. The result using log-MMSE exclusively produces a much cleaner semblance panel than just the SEGAN, as we can see in the first column on the right. Still, the cleaner panels for both the noisiest detached case were generated after applying the combination of both methods. In this graph, you can see a comparison of Great Circle Distance GCD for each method. To be considered a correct estimate, the GCD value must be below 10 degrees, which corresponds to the shaded region on the graph. Thus, it can be noted that only the results generated by the combination of both methods could provide an adequate forecast for all scenarios with different SNR values. Curiously, while the log-MMSE method produced interesting results for noisy scenarios, for less noisy cases, its results were some of the worst, even compared to the situation before the denoising process. Therefore, we can say that the combination of both methods seems to be quite promising, even for highly noisy scenarios, which tend to be more complex to work with. However, it is important to recognize that for in real-world deployment, different implementations may be required to increase the robustness of methods, including an expansion of the dataset user for training, testing involving the drone making flights in different scenarios, and include scenarios with crowds. We would like to thank IEEE for the opportunity to present this work to high-quality researchers. And we thank the event organizers to allowing this presentation to be done remotely. We also thank UFABC for the facilities. Last but not least, we thank CAPES and CNPq for their financial support to this project. Thank you all.